Hey everyone, so today we're going to be taking a look at section 5.1, which is about increasing and decreasing functions. So our goal for today is to determine where we can find local extrema. So if we were to take a look at this function here, we're going to get the function y equals f of x, which equals x cubed minus 3x. And its derivative would be 3x squared minus 3, which this can factor. We could take out a 3, and we could factor the x squared minus 1 into x plus 1 and x minus 1. Why is this important? Well, if we wanted to figure out where the slope of our function is 0, we would be taking a look at its derivative, because remember, the derivative of a function is the same thing as its slope. And if I want to find a horizontal line, I would want the slope to be 0. As in here, I would get x equals -1, and here I would get x equals +1. So if you take a look at our picture, here at x equals -1, and here at x equals 1, we are getting horizontal or not asymptotes, but horizontal slopes. So if we were talking about when a function is increasing and decreasing, it helps to look at the derivative of the function. I know this can be a little hard to see, but this right here is an f prime of x. The prime kind of runs into the f on that font. And they're saying that between x equals -infinity and x equals -1, that this function is increasing. And we can see that it's going up. Between -1 and +1, my function is decreasing. And that's pretty easy to see also. And then from +1 to +infinity, my function appears to be increasing again. So determining where a function is increasing or decreasing has a lot to do with the slope of the function or the derivative of the function. So this first box is kind of just summarizing what I was talking about where the function on the first slide was increasing, where it was decreasing, and then where it was increasing again. It's also pointing out that at x equals -1 and x equals +1, that the slope is 0, giving us that horizontal line. So theorem 1 talks about increasing and decreasing functions. It says for the interval from a to b, if the derivative is positive, so again, this is an f prime, I know it's hard to see. If the derivative is positive, then the function is increasing. If the derivative is negative, the function is decreasing. Sometimes instead of increasing and decreasing, people will talk about rises and falls. It means the same thing. And examples of functions that are increasing and decreasing can be seen over here. Essentially, going from left to right, if you are getting bigger as you go to the right, you are increasing. And if you are getting smaller as you go from left to right, you are decreasing. And when I'm talking about increasing and decreasing, I'm talking about the function itself, regular f. The derivative is telling us if we are increasing or decreasing, but the what is increasing and what is decreasing would be the actual y values. That's why our graph would look like the examples over here. So here on example 1, they're asking which values of x correspond to a horizontal tangent line. So this is a way of saying when is the slope 0 or when is the derivative 0. So the first thing I'm going to do is I'm going to take the derivative of the function 8x minus x squared, and I'm going to get 8 minus 2x. Next, I'm going to set that equal to 0. So 8 equals 2x, so that gives me that x equals 4. So which x value corresponds to a horizontal tangent line? It would be x equals 4. For part B, they're asking for which values of x is f of x increasing, and then when is it decreasing? So we need to look at this derivative again. Remember, if the derivative is positive, we're increasing. and if the derivative is negative, we're decreasing. And I find the best way to do that is to make a number line. We know that the slope is 0 when x equals 4. So this is a number line of f prime. And when x equals 4, the derivative is 0. So what happens if I plug in something less than 4? So my derivative is 8 minus 2x. So if I plug in something less than 4, let's plug in 0. I'm going to get 8 minus 0, which is 8, and that's a positive number. So my slope is positive over here. If I plug in something bigger than 4, so let's plug in 5, I'm going to get 8 minus 2 times 5, that's 8 minus 10, which is negative 2. I get a negative number. So I'm going to be increasing from negative infinity until I hit x equals 4, and then I'm going to decrease from 4 to positive infinity. So for C, they say sketch a rough graph of f and add any horizontal tangent lines. So this function doesn't look like I'm going to have any tangents. It's going to be a downwards opening parabola. That's probably some of our algebra 2 and pre-calc knowledge. So my function is going to look something like this. This will be at x equals 4. It gives me a horizontal tangent line. And yeah. Well, I guess when I was saying there isn't any, I was thinking asymptotes. There is a tangent line. The horizontal tangent line would be there at x equals 4. So example 2, I think there's a little typo in this problem, so we're going to have to fix it. It says, find the critical values of f. The intervals for when f is increasing, and those on which f is increasing. So it's asking about increasing twice. So let's just get rid of that. And on those where f is decreasing for the function. So they want to know, when is this function increasing and when is this function decreasing? So let's see here. We've got x, or f of x equals 1 minus x cubed. So if I want to take the derivative of this, this would be a chain rule. So f prime of x is going to equal 3 times 1 minus x squared times the derivative of the inside, which is going to be negative 1. So f prime of x equals negative 3 times 1 minus x squared. So if I want to figure out the critical values, so the critical values are when x is, or when the derivative is going to be 0 or non-existent, we're going to set this equal to 0. So negative 3 times 1 minus x squared is going to equal 0. So if we divide both sides by negative 3, I'm going to get 1 minus x squared equals 0. Let's take the square root of both sides. We get 1 minus x equals 0, so x equals 1. This is my critical value. So let's make a number line. The point, my critical point is when the derivative is 0, so that's what x equals 1. And I believe that is the only value that would make this derivative 0. So remember the derivative, f prime of x, is negative 3 times 1 minus x squared. So let's do a couple checks. So I need something less than 1. So what happens if I plug in, let's say, 0? If I were to plug in 0, I would get negative 3 times 1 minus 0 squared. So that's negative 3 times 1, which is negative. I know that if I plug in 1, I'm going to get 0. That's my horizontal. And then plug in something bigger than 1, so let's say 2. 1 minus 2 is negative 1, squared is positive 1, times negative 3 is negative 3, so it's going to be negative. So this function is decreasing everywhere except for where x equals 1. So where are we increasing? well, we're not increasing anywhere. We're just not increasing. So decreasing, that would be from negative infinity to 1, union 1 to infinity. So we're just decreasing everywhere. And if we were curious about what this function would look like, let's see, our slope is going to be 0 at x equals 1. So we're going to get the point 1, 0 right here. So my function would be decreasing, hits this point where it's horizontal, and then is decreasing again, which is something that's very similar to a negative cubic function, which if you take a look at our function, this is a negative cubic function, 1 minus x cubed. If we were to multiply that out, it would definitely be a negative cubic function. Local extrema. So a local extrema is a point where there is either a local max or a local minimum. Local extrema are also called turning points. So this is essentially like if you're looking at a graph, if you might not be the highest point on the graph, but if you are larger than the points surrounding you, you'd be a local max. Or if you are the lowest point on an interval, you would be the local minimum. And we're going to see quite a few examples of that. It says that when a graph of a continuous function changes from rising to falling, so increasing to decreasing, a high point, also known as a local maximum, occurs. And when the graph changes from falling to rising or decreasing to increasing, a low point or a local minimum occurs. So we're going to take a look at that too. So local maximums, the definition says that we call a point a local max if there exists an interval from m to n containing point C, where f of x is less than or equal to C for all values of x on the interval from m to n. For a local minimum, it is very similar. We call a point a local min if there exists an interval from m to n containing a point C such that f of C is less than or equal to f of x for all x's on the interval from m to n. So for example, if we take a look at the graph at the bottom and we asked where are the minimum values, well, if we looked at C2, C2 is smaller than anything on the interval from C1 to C3. C3 would be a maximum, a local max. It's bigger than anything from C2 to C4. C4 is going to be a minimum. And then C6 is going to be a maximum. So I circled the maxes in green and the mins in red. So notice that C1, C5, and C7 are neither maximums nor are they minimums. And the reason for this is the extrema happen when we go from decreasing to increasing. And then the maximas occur when we're going from increasing to decreasing. So if you take a look at the function, I'm decreasing. I hit C1, but then I continue to decrease. Therefore, it's neither a max nor a min. Then from C2, I was decreasing, but now I'm increasing, meaning that a local extrema occurred, and that's a min. From C3 to C4, the function is decreasing, so increasing to decreasing creates a max. And then from C4 to C5, I'm increasing, so that created a min. From C5 to C6, I'm continue to increase, and that's why C5 did not become an extrema. And then C6, I went from increasing to decreasing, so it created a maxima. And then I continue to decrease, which is why C7 would not be anything. So example 3, it says, use the graph of f to find an interval on which f of x is increasing and those on on which f of x is decreasing and any local minima. They're not asking for maxes for some reason, but they are asking for mins. So what I would do is I would find your highest points and your lowest points. These are your extrema because they make tangent horizontal lines. So this would be at x equals -1 and at x equals +3. And if you take a look, we are increasing, and then we are decreasing, and then we are increasing again. So where we change from increasing to decreasing, we've got a max. Where we are decreasing to increasing, we have a min. So increasing, we are increasing from -infinity to -1, and then also from 3 to +infinity. We are decreasing from -1 to 3. And then they ask for the local minima. Well, the local min is right here at x equals 3. The local min is at x equals 3. And if they wanted a y coordinate, we could actually just count that on this graph. It would be at 3, -5. So theorem 2, it's the existence of a local extrema. It says if f is continuous on the interval from a to b, c is a number in a to b, and f of c is a local extrema, then either f prime of c is 0 or f prime of c does not exist, as in it is not defined. So what this is saying is that local extrema will occur when the derivative is 0 or does not exist. But just because the slope is 0 or doesn't exist does not mean that you'll have a local extrema. It's one of those things that to be a local extrema, one of those things has to happen. But just because one of those things has to happen doesn't mean that you will be an extrema. You still need to check. But if I wanted to find or look for extrema, what I would do is I would look for when my function's derivative is 0 or does not exist. That is a good place to look for extrema. Because if they exist, they will have this property. So to find local extrema, what we're going to do is we're going to do something called the first derivative test. So the first derivative test says find all the points where the slope is 0 or does not exist. And then do a sign chart of the derivative to see when it is decreasing and when it is increasing. So again, these can be kind of hard to see, but these are all f primes. So we're looking at the derivative. When is the derivative decreasing or when is the derivative negative and when is it positive? Because that will indicate when f is decreasing and when f is increasing. So they say that if you go from decreasing to increasing, then you are a local min. If you are going from increasing to decreasing, you are a local max. If you go from increasing to increasing, you are not an extrema. And if you are going from decreasing to decreasing, you are also not an extrema. And the way I always tell people to remember this is you can always sketch this really quickly. Draw something that's decreasing and then increasing. So decreasing, increasing. Oh, it's a happy face, but there is a minimum value. If you are increasing and then decreasing, well, increasing, then decreasing, you're a frowny face, but there is a maximum value here. And then if you're increasing and increasing, it would be something kind of like this. There is no max, there is no min. Decreasing, decreasing, no max, no min. So you can always kind of do a rough sketch to verify these, but these are the two that we're looking for, maxes and mins. And it is when a sign change does occur. So kind of just a continuation of our first derivative test. Here are some graphs, and we are just looking at maxes and mins. So here, for decreasing then increasing, you are a min. Increasing to decreasing, max. Increasing, nothing. Decreasing, nothing. Here we're decreasing, we don't exist, and then we're increasing. So remember, we're looking at derivatives, so we can have derivatives that don't exist at certain points, but at that point itself here, this is still a min. Increasing does not exist, decreasing, max. Increasing does not exist, increasing, nothing. And then decreasing does not exist, decreasing, nothing. So again, the ones that we would expect to be maxes and mins are maxes and mins. Example 4, they say, given the function x cubed minus 6x squared plus 9x plus 1, find the critical values of f, and then find the local maxima and minima. So finding the critical values, this is where f prime of x is 0 or does not exist. So the first thing we're going to do is we are going to take the derivative. And this would be 3x squared minus 12x plus 9. And we want to set this equal to 0. So the first thing I would do is I would factor out a 3. That's going to be x squared minus 4 plus 3 equals 0. So I need to factor x squared minus 4x plus 3. So two numbers that multiply to be positive 3, but add to be negative 4. Well, that would be x minus 3 times x minus 1. So that gives me that x equals 3 or x equals 1. These would be my local extrema, or my critical values. I don't know if they're extrema yet, because I don't know if they're going to be maxes or mins. So for B, it says find the local max and min. So number line, and again, we're working with the derivative here. I know that my derivative is 0 at x equals 1 and at x equals 3. My derivative is 0. So I just need to check on these intervals. What happens when I'm less than 1, between 1 and 3, and greater than 3? So let's plug in some test values. If I am less than 1, remember I'm plugging into 3 times x squared minus 4x plus 3. So let's plug in something like 0. I'm going to get 3 times 3, that's a positive. If I plug in something like between 1 and 3, like 2, I'd get 3 times, well, let's see what happens if I plug in 2. F prime of 2, I'm going to get 3 times 4 minus 8 plus 3. That should give me negative 3, so I'm negative. And then something bigger than 3, it's going to be positive. If I plugged in like 100 squared is way bigger than 400, so this is going to be positive. Plug in any value bigger than 3 into the derivative, you're going to get something positive. So what do we know? Increasing, then decreasing. This guy's a max. Decreasing to increasing, that's a min. So these are the x values that produce the max and min. If we want to find the actual value, we should find our y value. And remember, the y value is f of x. So let's go ahead and find f of 1. So this would be 1 cubed, which is 1, minus 6x squared, so that's minus 6, plus 9, plus 1. And that is going to be positive 5. So our max is at 1, 5. Let's try f of 3. It's going to be 3 cubed, that's 27, minus 6 times 3 squared, 54, plus 9 times 3, 27, plus 1, should be 1. So my min is at 3, 1. Theorem 3 talks about the number of local extrema. So assuming that you have a polynomial of the nth degree, f would have at most n minus 1 local extrema. So let's say this was an 8th degree polynomial. It means that at most I will have 7 local extrema. If you are a third degree polynomial, you'll have at most 2 local extrema. So it's just the number or the degree of the polynomial minus 1. That is the maximum number of local extrema that you could have. So example 5, very similar to example 4, they want us to find the critical values of f and then find the max and min. So the first thing we're going to do is take the derivative, because we want to know when is the derivative 0 or does not exist. So my derivative here is going to be 3x squared minus 18x plus 24. So that's equal to 0. I'm going to factor out a 3. It's going to be x squared minus 6x plus 8. Two numbers that multiply to be positive 8 but add to be negative 6. Well, that's going to be x minus 2, x minus 4. So that tells me that x is 2 and x equals 4. These are the critical values. So if I want to figure out if they're maxes or mins, I'm going to make a number line. And again, I'm working with the derivative still. 2 and 4. Let's plug in some values to see what happens. If I were to plug 0 into the derivative, I'm going to get 0 minus 0 plus 24, so that's positive. Between 2 and 4, if I plug in 3, that's going to be something I need to calculate. So let's see, f prime of 3. I'm going to get 27 minus, I believe, 54 plus 24, which is negative 3, so it's negative. And then something bigger than 4, it's going to be positive. So I know increasing, decreasing, this has got to be a max. Decreasing, increasing, going to be a min. So to find the actual values, I need to look at the y values. I need f of 2 and f of 4. F of 2, so if I plug in 2, I'm going to get 8 minus 36 plus 48 minus 10. So this is going to be 10. So my max is at 210. And then for my min, I need to know what is f of 4. So f of 4 cubed, is going to be 64. Minus 9 times 16, that's going to give us 144. Plus 24 times 4, 96, minus 10. So 64 minus 144 plus 96 minus 10 is 6. So my min is at 4, 6. These would be my values. So some closing thoughts on this section. We're going to continue to do graphing and working with extrema for quite a while, actually this whole chapter. We're going to see something called an absolute max and an absolute min soon, and that's kind of like what they sound like. It would be the biggest value is the absolute max, and the smallest value would be the absolute min. All in all, like this is stuff that you could probably do with algebra. If we were to just graph the function, it's pretty easy to tell where a max and min is. But our goal is to be able to solve these without having to graph them. If they just give you a function, can we figure out where their maxes and mins, where is the derivative 0? And of course, using calculus, we know how to do this stuff. And that's what this exercise is all about. It's something that you could brute force with like a graphing calculator. But this is going to be much, much faster. And going forward, that is something that's going to help us a lot. Is we need to be able to do this without having to graph it. Because some of the functions we might deal with will be really hard to graph. So again, the homework will be posted. And if you got questions, feel free to reach out.